So we're going to talk about energy transformations in a simple circuit. A simple circuit is one that just has one closed loop with a battery or a voltage source and also something else, in this case a resistor that's connected to the battery by wires. And what I've drawn for you shows the voltages at different places in that circuit. We always have to have a reference point for 0 volts, and I've defined that to be the negative side of the battery. And we have a 1.5 volt battery, so the positive side has a voltage of 1.5 volts. And we're going to call that difference delta V bat. We know that in the wire the voltage does not change, so delta V wire is 0. And over here on the other side of that, where the wire is connected to, is therefore must also be 1.5 volts. And down here, which is connected by a wire to the negative end of the battery, must also be 0 volts. I've also drawn inside the battery and inside the resistor electric field vectors. We know that if there is a voltage difference, there must be an electric field that's causing that voltage difference, and the electric field always points towards the lower voltage. So there's those vectors here and also here. There's no electric field in a perfect conductor, and so E equals 0 in the wires, assuming they're perfect conductors, and that's why there's no voltage difference. So I've also drawn the positive conventional current I, which represents the hypothetical flow of positive test charges around this circuit, and they would be coming out of the positive end of the battery, traveling through the wires, through the resistors, and through the other wire back into the negative end of the battery, just flowing in a continuous loop. Okay, so we were going to talk about energy transformations, and so we're going to use the basic relationship that electric potential energy is of a charge in an electric field is Q, which is the amount of charge, times E, which is the magnitude of the electric field, times H, which is the height in that electric field. And since E times H is what we mean by voltage, we can write that electric potential energy as Q times voltage. And that's very analogous to gravitational potential energy of a mass in a gravity field, which we know is mgh. So that's like QEH. So before we go back to the circuit here and talk about electric potential energy, let's talk about the analogy to gravity for a minute. So I've drawn another picture here, which on a snow day like today is very appropriate. If you've ever gone skiing, you know that you start at the bottom of the mountain, and then there will be a ski lift that lifts you up to the top of the mountain. So, and we're going to assume in the picture that we're talking about that these skiers at all times are moving at a constant speed. So they never stop, and they never go slower or faster. So they get on the ski lift, and the ski lift lifts them at a constant speed. When they get to the top, we're assuming that the top of this mountain is flat, and it's also ice, so there's absolutely no friction. So they hop coasting along the ice.
And when they get to the other side of this picture, then they go downhill. And when they go downhill, if there weren't any friction, they would gain speed. But we're going to assume that there's a lot of friction because of the bumps in the hill. And those are called the moguls if you've ever gone skiing. So these skiers bump up and down on the way down, and they maintain that constant speed. When they get to the bottom, they just make a turn, and they keep moving at that same constant speed because the bottom of this mountain is also ground with ice and no friction, so they keep a constant speed. They go back to the ski lift, and they just keep going around and around. So that's a picture that might help you think about what's going on in the electric circuit. The skiers are supposed to represent positive test charges. Now when we think about the mountain with gravity, these
these skiers, which are masses, are gaining gravitational potential energy. The Earth skier system would gain gravitational potential energy when the ski lift lifts them up. But the ski lift has to do some work. It's an external force that has to do some work to lift them up there. So once they get to the top, they have higher gravitational potential energy because they're at a higher place in the gravitational field. When they ski across the top, that's a level surface. They're not going higher or lower, so they're maintaining a constant high gravitational potential energy. When they ski down, they're going to lose that gravitational potential energy, and by the time they get to the bottom, it will be gone. Well, where does that energy go? It has to go somewhere. When we have friction, that is going to convert gravitational potential energy into thermal energy of the skier and the hill in this mechanical situation. And so the hill is going to get hotter. You might melt some of that snow on the hill. And then on the bottom of the mountain, they're maintaining that low gravitational potential energy. They're not going higher or lower. They're just coasting at a constant speed. So we're of a skier.
They're going to gain gravitational energy here, so I'll represent that as work by the ski lift getting converted into gravitational potential energy of a skier. And that work by the ski lift has to ultimately come from some other energy source. And so the ski lift gives the skiers gravitational energy, and then the moguls take away that gravitational energy, converting it into thermal energy. So there's a continuous process happening. Now these skiers you can think of in our circuit as positive test charges. So when we go back here to the circuit diagram, the battery is the ski lift. The electric field is analogous to the gravitational field of Earth in the other picture. And this battery has to do some work. It has to provide energy to lift a positive charge from the low voltage place to the high voltage place. So we can say that the work of the battery gets converted into electric potential energy of a positive charge over here. Another way to think about that is that the battery gets its energy from stored chemical energy. So you could say that there's some chemical, some stored up chemical energy in the battery, and that's what gets converted to the electric potential energy. And eventually a battery will use up its chemical reactions, and that stored energy will be no longer available, and the battery won't be able to lift those charges anymore to give them energy. Once the positive charges are here in this wire, they're just going to move at a constant speed. There's no resistance in wires. There's no friction. So they just maintain that constant speed like skiers on a level slope. When they get over to here, they're going to encounter resistance from this resistor, but there's also going to be an electric field pushing them down to lower voltage, just like the skiers had a gravitational field pushing them down to the bottom of the mountain. So they're going to lose their electric potential energy when they ski down or move down to the lower voltage place. And in a resistor, there's lots of collisions of the charges with the atoms of the resistor. Those collisions cause transfer of the electric potential energy into thermal energy, and the resistor will get hot. And then when the test charges get to the bottom wire, they just move again at a constant speed in the place with no resistance back over here, and then they're ready to move up again. The battery will give them some more energy. So in this circuit, we have a transformation of chemical energy to electric energy in the battery, raising charges to higher potential energy. They carry that energy over to here, and then they're losing electric energy, and it will be converted to thermal energy in the resistor, and then the cycle repeats.
we're going to do one problem with this picture, but before we do that, you might be wondering why we're talking about the positive test charges, because we want to believe, and that we know from experiments, that in fact what's actually happening in the wires is negative charges. Electrons are coming out of the negative end of the battery and flowing this way around the circuit. Well, we talk about positive charges because Q is a positive number for a positive charge, and it's therefore positive charges gain electric potential energy when they go to the higher voltage place, just like the NASA's, the skiers, gain gravitational potential energy. Negative charges, which flow this way, actually the same story that we just talked about would apply to them. However, when they get to, so negative charges are going to experience a force towards the higher voltage in that electric field. So we can say that negative charges are going to fall uphill. They're going to lose electric potential energy when they go to the higher voltage place. But the end result will be the same. They're going to be losing electric potential energy here as they go through the resistor, converting that into thermal energy. And when they get over here, they will have less electric potential energy at the high voltage place, and the battery will lift them this way, uphill. The battery will lift them, the battery will lift negative charges downhill towards the lower voltage place. But when they do that, they actually have more electric potential energy here. So that's another example of the electric potential energy formula, but for a negative charge. All right, notice that there's no absolute value here when we talk about the electric potential energy formulas. So Q could be plus or minus. All right, we're going to do one problem with this example. So let's think about a single electron that's going to make a round trip. And that single electron is going to start at the negative end of the battery. It's going to go through a wire. It's going to go through that resistor, come back through this wire, and then go through the battery. So what I want you to figure out is calculate the change in electric potential energy of our electron plus electric field system in the resistor in the picture I just showed you, and what would be the change in electric potential energy of that electron plus the electric field in the battery. And your answer should make sense in terms of its sign. We know that that electron is losing electric potential energy here, but gaining electric potential energy over here. So that should tell you one of these is going to come out positive and one of them is going to come out negative. All right? So think about a single electron. And so you'll get an answer in joules for those. All right? Then the other thing I want you to do is think about, for a current of 1 ampere, which is 1 coulomb per second, I want you to figure out how many electrons per second are passing each point in the circuit that we just showed. All right, so you could figure that out. How many electrons per second are passing each point? And then, one final thing. So I want you to calculate the rate at which the battery provides energy to the circuit if the current is 1 amp. Now, a rate means the change in electric potential energy per time. You're going to find how much how many joules of electric potential energy per second the battery is delivering. And that's an easy calculation to do. We know that change in electric potential energy is simply how much charge times the change in voltage that that charge moves through. When we divide by time, we get the rate. However, charge divided by time is nothing but the current in coulombs per second, or amps. So if you take the current times the voltage difference of any place in a circuit, you will get the rate at which electric potential energy is being given to the charges in that part of the circuit. So I want you to find the rate at which battery is providing energy, assuming the current is 1 amp. The units here would be joules per second. And you can see, and that's also called a watt, which is capital W. And in electrical problems, a watt must have the same units as current times voltage difference. So a watt is an amp times a volt. Okay, so that's your assignment for